Hello, and welcome back to our Big O Notation video series. I'm Charlie Armitage, and today I'm going to be teaching you about merge and heap sorting. To start, both of these sortings have the average case of O and log n. This means that it will take less time to sort algorithms and will be much quicker compared to the previous generations mentioned in episode 2. Now on to merge sorting. First up, we have merge sorting. And merge sorting is known for its stability and efficiency. Merge sorting also has a thing called divide and conquer, where you divide the set of numbers into different arrays as small as possible, or if each array has one number. So let's start out with 3, 4, 6, and 2. So we have 4 numbers here, and we want to divide them in half. So we have 3, 4 in one, and 6 and 2 in the other. Next up, we have to divide it again, and to make sure it's as small as possible, plus each array has one number. And so now we compare the numbers and we make sure that they are lined up in order. So first up we have 3 up here. Is 3 smaller than 4? Yes. So we leave it there. But before we write down 3, we want to compare it to the other side too. So we do the same work. This is the first part of the original half of the array. So we compare it to 6, which was the first half. Is 3 smaller than 6? Yes. But we have to do it for the second one. Is 3 smaller than 2? No. And so now, based on logic, we can know that 2 is the smallest number, and we run through it again. Is mixed, and we go to this side. Is 6 smaller than 3? No. Is 6 smaller than 4? No. And is 3 smaller than 4? Yes. And is 3 smaller than 6? Yes. And so we know that 3 is the next smallest number. Compare 4 to 6, 4 is smaller, and then we each move it up once we compare it. So like let's write it down here again. So 3, 4, 6, and 2. When you're trying to compare numbers, you want to move the number up and compare it to the below number and make sure it's the smallest. And once you do that, you just continue to do this process until there are no numbers left to merge. Here's what merge sorting will look like on C#. So here is the C# code for merge sorting, and the basic summary is where you're given the numbers, you're splitting them into halves, and then eventually just checking in the order of merge sorting just to see if one's smaller than the other, and eventually finding it in the right order, like it's shown on the whiteboard. Next up, we've got heap sorting. Now, the thing you need to know about heap sorting is that it's pretty complex and complicated, but it does take up less space than merge sorting. So I'm going to give you an example problem and give you a better understanding about how it works. So this thing is called a heap. It's kind of like a data table, but if you think about it, it's kind of like a family tree, where the top of here is the parents and these are the kids. And like a family tree, the parents are older than the kids, so you want the bigger number to be older than the smaller numbers. And so we can start out by this. So we want to go through this, and 6 right now is the top number. We want to get the biggest number. If 6 is already the biggest number, then we can move it off to the side, and that can be our last number. And so, but 6 is not the largest number. Here's what heap sorting will look like on C#. So this is the heap sort C# code, and basically what it's doing is you're given random numbers. These are different from what I wrote on the whiteboard. Then making a array /heap/ family tree, and assigning a random number to each spot, and basically the same method that we did on the whiteboard, where you move the largest number to the top, moving it to the right to make it the largest, and eventually get smallest to largest from left to right on your array. Who's ready for Mythbusters? But in this term, fast or slow? Well, we're determining the popular belief O n log n, which is the merge sort, is actually faster than O n, and O n squared equals the insertion sort. So we're determining that to the test. So the less amount of steps you will take for each method means it's faster. So to start, we're going to have 2 identical arrays, and we're determining which one has less amount of steps just to make it fair. So we're going to start with the merge method. So when splitting in half, each one of these is 2 steps since you're splitting it. And so now we want to determine for the first group array, is 3 smaller than 2? No. Is 3 smaller than 5? Yes. So you would put it here, and you have to put it up to make sure. Remember from the merge method earlier. And so that takes 3 steps. And so That's not bad, but let's see which one's quicker. This determines the next steps. So 3, 2, 5. We're going to use the insertion method for this. So first, for the insertion method, you want to use the second number and determine if it's smaller than the left number and the big number. So if it's smaller than 3, then that means it's smaller than 3. So what you want to do is move it here, and that's only one step. And as you can see, 2, 3, 5. But we're not done with the equation just yet. We need to make sure that it's actually smaller than 5. So we look at the second number, which is 3, and we can see that it's less than 5. So that means we're all done. It only took us that one step. And so insertion sort actually is quicker, but you might be curious, why? Because big O only tells us how algorithms grow at large input sizes. For small or nearly sorted data, the constant factors and simplicity of quadratic algorithms can make them the better choice. So next time someone says O n log n always wins, remember, the context matters. Myth busted. O n log n is actually slower than O n/O n squared. That's the end of the lesson. I hope everyone liked learning about O n log n in merge, heap, and insertion sorting, and how it compares to quadratics in certain scenarios. We'll be back in episode 4 with Max talking about quicksort pivots. Until next time.